The other one is a quality, and the quality we can find relating this scale here to the number we know, right? So this is easy to do. We've done a lot of times here in the channel too. And all I need to do is to find a quality, is to relate the 1360 that I found minus the liquid enthalpy, which is 135.4. And we're going to divide that by the whole scale, and the whole scale is the enthalpy of the vapor, saturated vapor, I should say. And the same 134.5, I insist on 4 here, 5.4. And that's going to give me about 94.36%. Okay, so much closer to the saturated vapor than the saturated liquid, as expected. So this is the answer for the properties of the outlet. This is the other part of the answer for the property of the outlet. Now, the last piece of the puzzle is, what is the area? The area of the exit. So there, if we didn't know the density, if they didn't give us the density, then what we would do is go ahead and grab the properties off the table. But what we know is this is a saturated mixture, and we have we're given the density from the start. So we can use the density to relate what is the specific volume, and we can calculate the area. Okay, so we don't even need to use the tables because this was given to us from the start. Okay, so how do we set up this idea? Well, we have been given that the ammonia exits with a certain density, right? And density, as we know, is the inverse of the specific volume. And we need to find the specific volume of the exit to be able to grab the cross-sectional area. However, note that this is the density of the fluid. So the F there stands for fluid, right? So therefore, the liquid, I should say. So saturated liquid. So what we know is that this is a mixture, and we know that the saturated liquid density is 651, which is the inverse of this. So let me go ahead and write that this is 651. That's kilograms per meters cubed. I'm going to grab this information here and take it with me all the way down here. Okay, what else do I need to remember? I need to remember the cross-sectional area. If I have cross-sectional area and I have a velocity going through it, then the perpendicular to it, orthogonal, then that the cross-sectional area times the velocity will be equal to my volumetric flow rate. And the volumetric flow rate is related to the mass flow rate by the definition of specific volume. So if I'm looking for my cross-sectional area, what I can do here, given the information I have, is take the mass flow rate, the specific volume, and divide that by the velocity. Okay, note that I have this. What I don't have specifically is this, but I have all the information I need to grab it, right? So what I'm going to do is first grab this, and then once I have that, I can grab this. So the specific volume is a combination of the one for the liquid and the one for the fluid. The one for the fluid I was given, and the one for the liquid I can grab here off the table over here. So this guy here is, if everything were vapor, if I had a saturated vapor, then this would be the specific volume. But I don't have all saturated vapor. I actually have 94.36 vapor and some leftover liquid. So I need to combine those two guys. Okay, so my specific volume for the state 2 will be a mixture of 90, how can I do this? 90, the inverse of this, so 1 over 651, which accounts for the liquid, plus the 94.36% times the difference between the two. And the difference will be the 4185 minus the specific volume for the liquid, which is just the inverse of 651, and this gives me 0.395 meters cubed per kilogram. So that's the specific volume of the mixture. Note that this is exactly the same, if you prefer to think in a different way, this is exactly the same as saying, okay, I'm taking 94% of the 0.4185 plus 100% minus that, exactly that 94.36%, that is the rest, and then times the specific volume of the fluid, which is 1/651. It's exactly the same math. Okay. And then with this, I can now go ahead and calculate my cross-sectional area, which will be 0.01 times my 0.395 divided by my 450. Unit-wise, what do we have here? Unit-wise, we have kilograms per second. On the bottom, we have meters per second, and then we're multiplying all that by meters cubed per kilograms. So kilograms and kilograms, seconds and seconds. Then 1 meter with the meter cubed gives me meters squared, which is great because that is what I'm looking for. So 877 times 10 to the minus 6 meters squared. And that is the cross-sectional area at the exit of the nozzle. All right, so this does it for this problem. I'm going to have a look if ChatGPT can solve this, make some comments there. And if this was useful, consider giving it a like. If you have any questions, as per usual, just leave them down below in the comment section. And we'll talk soon.